take away.
Oh boy. Okay, so we already live. So Akil, you could go ahead and start us off. Go ahead and let the people know who you are as we start to get into our conversation tonight and tap into our math genius.
Yes, so Akil Parker, father of three, founder of All This Math, and CEO of All This Math that has a mission to improve the relationship between the Black community and mathematics overall. And we offer different resources for youth, for parents, for teachers, that being books and the YouTube channel, the All This Math YouTube channel, where we put up content ranging from arithmetic all the way up through calculus one and everything in between. And yeah, and we want for people to get over the issues and the challenges that they may have with mathematics.
Absolutely. Thank you for that. Now I'm gonna tell y'all for the people that come in and join us, Akil is not playing out here in these mathematical streets. He is everywhere. Every time I turn around, you got a documentary, you got an interview, you got a new video. I said, hey, he eating it up. He's leaving no crumbs. I love it because I feel like we need it. We need to have some positive conversations centering on mathematics. I'm tired of hearing about negative stuff. And I just told somebody last week about, how school has started back. So parents are starting to talk about their challenges with homework and stuff. And I was like, y'all, I know when you get up here and you start talking negative about math homework, your posts go viral because everybody can relate. But
Uh-huh.
let's dial it in and let's keep it positive. Let's keep it positive. We got to change the narrative about this math homework and just mathematics in our community in general.
Yeah.
Dana, what's up?
What's up, man?
Listen, what's up, y'all? It sounds like y'all already cooking, so I'm ready for the party.
We just getting the groceries ready. Let people know who you are.
Just bringing them out the car.
Right, right.
Go ahead and introduce yourself, Dana.
Dana Harris, father, educator, chief academic officer of Young Gurus Math Tutoring, online math tutoring platform, as well as I have a YouTube channel, Young Gurus Math Tutoring. Go check me out. Not quite the same thing that Akil's doing, but that provides diversification for the
Mm-hmm.
parents and students.
Yeah.
Absolutely. Y'all doing good work. Y'all out there in the streets. Y'all getting it done. So greetings everybody. Lanisha here, owner operator of Bud and Bear Fruit Education. I'm out here just trying to make sure that these kids and their parents understand that they are capable of being successful in mathematics. Okay. Just because somebody that you knew or somebody that you knew did not have a good relationship with mathematics does not mean that you do not. So I am trying my best to make mathematics more accessible for all. So without further ado, we're gonna go ahead and get into tonight. Tonight, I really wanted us to go conceptual. I wanted us to kind of talk about some things and why certain things should make sense. So this is a conversation. I want to hear your thoughts about these things. And then when people join us, I would love to hear their thoughts in the chat as well. So I am starting off tonight. This is our Mythbuster. I ain't got time for that. So before I tell you my thought process behind this quotation, I want to know what is the first thing that comes to mind for you guys as you see this alongside this picture.
So I see that it looks like a child, but I'm thinking that that's something that, a parent would say, in terms of if they're encouraged to learn the math that their children are responsible for in school. And it really is like, it is a kind of a prevailing narrative, unfortunately, because, it's like you're going to suffer the consequences of not making time for it. Like, whether they be short-term consequences, intermediate term consequences, long-term consequences, not taking the time to, really just try to gain an understanding of what your children are being charged with learning how to do is going to rear its head, in terms of whether, I mean, it could be something like, your child may not qualify for certain opportunities down the road in the future. And then, you know, because they don't have another choice, they may have to live with you when they're 25, 30, 35, 40. You know? So, you know, take that time. I know that's like an extreme, but, and not to say that, and also not to say, because I know somebody's gonna hear that. The first thing they'll say is, well, you know, we shouldn't be kicking our kids out at 18 and all of that. Now, you know, I hear you, I'm with that, but I'm talking about something more different, you know, because if, you know, your child may not have the option. They might not have the ability to be, you know, self-sustaining and self-sufficient, because they weren't developed academically in a certain way or to a certain extent. And as a parent, maybe we didn't take the time to try to facilitate that when they were young, you know. And I think that could be, it's a cautionary tale. There's a lot of cautionary tales out there, you know. And I think as a community, we got to start like reverse engineering a lot of our situations that we end up in, and looking back and saying, well, you know, how can I move differently, or how can I tell people, you know, about, you know, what I could have did differently or what I should have did differently. And this is, I think, one of those things when we say we don't have time for stuff.
Dana, what you think? What comes to mind for you when you see, I ain't got time for that?
What comes to mind is a parent struggling. And I'm going to create a narrative. We used to do, side note, we used to do this activity when I was doing, when I was leading these camps by Nesby, and it was the Seek camp, right? And one of the training activities we used to have to do with our team members is there was a screen and it had several different faces of students, and they had to pick a face and describe who that person was. And it's basically showing our bias and things like that, right? So I mentioned that because right here, this is, I'm going to practice that live, right? So this young lady, she is obviously on her phone, pretty much telling her mom at the last minute, oh, mom, let's say dad too. Mom, dad, I've got homework, or whichever parent helps her with the homework, right? And so we're going to say it's two parents. And they're in the kitchen, and one of the parents says, math homework, I ain't got time for that. Because they don't want to deal with the frustration that they felt that comes along with the homework. And maybe it's causing some friction between the parents and the child, because they feel like it's a struggle for them, and they don't want to show weakness to their child. They don't want to show, like, maybe these parents, or one of the parents, the parent that's saying that, maybe they don't want to show that they can be wrong, or they don't want to show that they don't know something. So instead, what do? Avoidance. I ain't got time for that.
Okay. Thank y'all so much. You guys looked at this from the parental perspective. When I typed it, I was thinking about the child. And the reason why I thought of this today is because what I'm seeing in classrooms is basically kids that, even if they don't say this specifically or directly, the way that they act in relation to work assignments is like they don't have time for it. So the kids are, instead of them taking time to understand, taking time to explore, taking time to figure things out, they want to get straight to the answer. And oftentimes that leads to a whole bunch of holes and a lack of understanding. So I wanted us tonight to take an opportunity to look at some of the things that kids are learning, and I want us to make it make sense. People are always saying it, make it make sense. The math ain't mathing, all of these different things. I want us to look at some things that kids are responsible for learning, and I want us tonight to make it make sense. So we're not going to delay anymore. We're going to go ahead and jump into it. So our first one that we're going to go conceptual with is area. So I'm presenting you guys with a whole bunch of different shapes, and somebody said I knew it in the chat. I'm presenting you guys with a whole bunch of different shapes, and students are tasked with finding area of these various figures, right? These two-dimensional figures. So my thought to you guys, or my question to you guys is, how can we make finding area make sense? Make it make sense.
I got an explanation for it, something that I didn't always understand when I was younger. So conceptually, we think of area, we think of squares,
Okay.
right? So I'm thinking of on any flat surface, how many one by one, and then we got to choose the units too, because we could be talking about inches, we could be talking about centimeters, we could be talking about feet, yards, but how many of those can fit into this space,
Okay.
right? So how many squares can fit into this space? So just to think about that, I think it kind of can clear some things up and make some of the more challenging questions that we might see on a standardized test seem more attainable if we think about, because oftentimes we'll learn like, and I like early in my career I used to be famous for this. Like I didn't have the conceptual background, so I'm just like, all right, what type of shape is it, and then access your database of formulas or look on your formula sheet and just go to the formula. Or if it's a rectangle, length times width. If it's a triangle, 1/2 base times height. If it's a circle, pi r squared, right? But that has no real, if you don't have a conceptual understanding of like what area is, like if I can't really explain to you like, okay, once I get the number, what does that number really mean?
Right.
You know what I'm saying? Like, and unfortunately, like a lot of teachers are like that. And I'm gonna say this too. If anybody's watching, like when I go hard on teachers, um, it's because I'm really a part of it. I'm really talking to myself, my early career self, because I get it, like I relate to it. But I'm like, so I know how beneficial it is to actually do the work of becoming a serious math practitioner, because it's going to help your teaching, it's going to help your students. A lot of us like don't do that. They just like kind of settle for, I know what I know and I could teach the curriculum.
Mm-hmm.
But your students not really going to learn. You got to develop within yourself that conceptual understanding, so that way you can relate better to different students that are coming from diverse backgrounds with diverse levels of understanding, different types of deficiencies, even different types of surpluses of knowledge, right? You got to really know it. You got to really know, like really be in it. So when I think of area like these days, I first start with, okay, well, how many square units, are on this floor, on this wall, in this flat 2-dimensional space. And it also then it will help for a child to understand or a student to understand, oh, this is why when I write my units, I always got to put the exponent too, because it's squared, right? That's just a way to like help them remember that. But yeah, when I think of area, I first and foremost try to think of the concept, like, okay, how many square units are in this space? Whether it's inches by inch, centimeter by centimeter, foot by foot, yard by yard, mile by mile, whatever.
Okay. Dana, what you thinking?
Conceptual. I'm gonna go simple on this one. I think about how much space something takes up. So in this case, if it's a flat object, then the space that it takes up is only 2-dimensional, length and width. So similar to what Akil said, how many of those little small squares on that grid can cover up one of these shapes? And so when we look at some of these shapes, they're not squares. So now you might have some shapes that a full square or more than one full square covers, but then there's some shapes, for example, the purple trapezoid, it's not going to be covered in full squares. So I'm looking and I may be able to cover that purple trapezoid with 4 of those squares, but then the right sides that kind of stick out, I may have to like cut a square in half diagonally to cover that space. So I just think about how much space something takes up. And then when we since we're just talking about area, that's all 2-dimensional. So all of these are going to be flat, and how many units, whether it's these squares on this grid that's on the screen, whether it could be anything. Let's say you take Uno cards. How many Uno cards can cover this shape? How many, whatever it may be. And so how much space something takes up, or how much space does it take to cover something even?
Right.
So that's the thing that I think about conceptually.
All right. So a student is learning. Where do you think they should start in this? And obviously, this does not cover all the shapes that exist out there in the world, all the 2-dimensional shapes. This is just some that I felt like students are seeing most often in 6th grade. So where would you start, or what do you think it's easiest for a student to kind of follow the conceptual pathway? Where would you start?
I would probably just go and cut out little squares. And well, I would start first of all talking to them about units of measure.
But which of the
Inches.
shapes would you start with?
Oh, probably rectangle, most likely.
Okay.
If not, either a rectangle or a square.
Okay. Akil, which one would you start with?
I probably start with the square, and then take it to the rectangle. But then,
Wow.
and I might, well, because the area is going to consist of squares, but then I would like probably proceed to the types of problems where you might have to have half of a square over here, a third of a square over here, especially when, and then like maybe when we get into the circles, and also show how like that's why like sometimes the area of a figure is not going to be a integer or a whole number, because you could have like a piece of a square or like a
Right.
fraction of a square, you know. But yeah, I probably do that. The trapezoid is interesting to me though.
Yeah.
The
Yeah.
trapezoid is interesting.
So somebody in the chat said they would start with the triangle. The triangle probably would be maybe third on the list, possibly fourth. Where would the triangle fall for you guys?
I would probably I would go third, and here's why. Because the trapezoids, the purple and the yellow trapezoid to be specific. So although they look a little different for the viewers, they're the same shape, right? They have a set of parallel bases, meaning that top and bottom in this case. But then if you notice the sides, they're a little different. If we visualize this, then we can cut both of those trapezoids into either a rectangle and multiple triangles, or a rectangle and a single triangle, or we can cut it into a square and two triangles, or a square and one triangle.
Yep. So
So that's why I say triangle third, because now if they've already been taught about squares and rectangles and triangles, then now we can say, hey, let me show you how we can take this square and this triangle and put it together and create a new shape called a trapezoid.
Okay, so let's just say we start with the square, right? And we talk about how all the side lengths are equivalent, all that good jazz. We're talking about square units anyway, so we put the square inside the square, okay, boom. Then we can kind of stretch it out a little bit, and now all the side lengths are not equivalent. We talking about quadrilaterals, right? So then maybe we go here, and maybe the students can kind of see what the differences are between maybe the angle measures of those two shapes versus this third shape, how it looks a little different. And then we can go here, something like that. And then once they see that two triangles can create that quadrilateral, because I mean, we can do it in the rectangle and the square as well. But then once we see the relationship, I think it makes sense why we do what we do when we're finding the area of a triangle. And what I've seen is the students, the issue they always have when they're calculating the area of a triangle, they don't ever want to divide by 2. They always base times height, base times height, base times height, lip times width, and they don't ever want to do that final step. So like if we could transition and they see that relationship, maybe it can make more sense, and maybe it'll start to click. And then like you said, when we get to the trapezoid, like you, I probably would do those on the end. And the isosceles one, I'm probably going to do some decomposing and rearranging.
I have a question.
One big rectangle. Yep.
How do y'all feel about, I guess, maybe not abandoning, but switching up from finding the area of a rectangle or square by length times width and going strictly base times height?
That's what I do.
That's what you do. So you don't do length times width at all?
Usually no, just because it's easy to transition to the triangle.
Right.
And then even when you get into volume and they do the big B, which is the area of the base, times the height for the layers. So when I say base times height, I do always relate it back to length times width, because I know in elementary school, that's all they say, length times width.
Length times width, okay.
So I say base times height because for me, it's easier for me to think about which one would be the base and which one would be the height. Sometimes when I look at a shape, this is probably going to sound real crazy, but sometimes when I look at a shape, I'm like, well, dang, if I'm looking at the length and width, which one Which one gonna
I-
be like the which
Hey,
one?
I'm the same way. I'm the same because I think when I think width, I think of how wide something is. So I'm more of that
Correct.
horizontal. But in some books, depending on who wrote the book, the textbook, the width might be vertical.
It is.
And it's like, but then we understand that like, okay, technically it doesn't matter because you could like your thing, rotations. You love the rotations, right? The shape could be rotated. And if you rotate it, then that's out the window because now what used to be horizontal is now vertical now.
Correct.
So then we can't even rely on the fact that the verbal connection between width and wide.
Right.
So it's like, yeah.
And
Well,
then
the question that comes
oh,
the
go ahead.
question that comes to mind for me, something you said, Niche, is about kids forgetting to divide by 2. How
Mhm.
much of that do you think is affected by the teachers that teach it as 1/2 times base times height versus the teachers that teach it as base times height divided by 2? Although mathematically we understand it's the same thing,
Mhm.
but that's just a random thought that came to mind as to why some kids may forget that step. Because if I'm a 4th grader that had a teacher that taught it as 1/2 base times height, and then I get to 5th grade and I got a teacher that teaches it as base times height divided by 2, maybe there was some confusion in there that has been added to the fact that maybe my guardians didn't weren't adamant about me sitting down and practicing multiple times a week during the summer months.
Right. I definitely think there's probably some challenges with that, especially because kids don't necessarily, as much as we would like them to, they don't relate the 1/2 as the same thing as dividing by 2. So if I'm hearing 2 different things, it's going to be hard for it to really stick. You know what I mean? I think that consistency in the language that we use, like you said, it does present challenges. We ain't being consistent just as the teacher.
Mm-hmm.
So that's a good point. That's a good point. But yeah, so the first one we started with out the gate, we talking about area. So you guys said understanding that we are talking about how much space is filled up for a 2-dimensional shape, no overlaps, no gaps, and we have a nice little pathway here that obviously is flexible. We can kind of change it up a little bit, but really focusing on the relationship between the shapes so the kids can kind of make sense of why am I finding it this way? Why am I solving for this in this way? All right. Next, let's go to volume. How can we make this make sense?
How much space does it take to fill it up?
Mm-hmm.
So now we've made something, instead of it being flat, it's now I don't have, I got something right here. Instead of it being flat like this, boom, I could twist it, turn it, rotate it, or whatever. But then now, when I get something so this has 2 dimensions. But then when I bring in that 3rd dimension, you see what I'm saying? So now this book has that 3rd dimension. So how much space can I put in between all this that it takes up? Or like if this wasn't a book and it was just this shape, but it had the sides almost like a box, how many of the now 3-dimensional blocks does it take to fill in that? So if we take these flat squares that's on our grid on the screen, and then we make them, I wish I had my base 10 blocks, but I got some dice right here.
Why would I go and pull this?
You see what I'm saying? So that's what mine ain't near me, but I take now these little cubes, these little dice, and I fill up the space. You see what I'm saying? In this, as if this was a box. And so how many of these little cubes, these 3-dimensional cubes, can I put inside this 3-dimensional figure?
Right.
And once again, with this being a triangular prism, the thing is you can put a bunch of these little small squares in there. But when we start getting to the corners and the edges, we're going to have to cut a piece of this cube to fill up that space.
Yeah. So whenever I think about, and you said your base 10 block, whenever I think about volume, I think about, like, if I was pouring liquid into a glass, I'm going to cover the bottom first.
Absolutely.
And then as I fill it up, it's like layers and layers of whatever it took for me to cover the bottom.
Absolutely.
So I love using the 1,000 block because it shows them those different layers that it takes for me to create this shape, this cube.
Right.
So thinking about volume, that's the reason why they use as I was saying earlier, you may see some formulas or equations that look like this. Have y'all seen this one? Where big
Yes.
B is the area of the base,
Yeah.
and then the H
Right.
represents the layers.
And I
Yeah.
think even that we have to be specific when we're presenting that to kids because they're used to seeing little b. Okay,
Correct.
well, what's big B? And then now I gotta specify that's the area of the base. You see what I'm saying?
I'm glad that you brought that up because a lot of times whenever, like when I'm walking through classrooms and I see kids taking notes, they think I can write the letter any way I want. Like if I
Right.
see M, or if I see whatever, I can change it to a cap, I can change it to lowercase. And I'm telling them, no, you need to write this as this. This is what represents that. Like when you change it, you may potentially change what it is. You know what I mean? And I think it's very important that we kind of talk about like attending to that precision and not making something up along the way. Because I think that is something that can be confusing or present challenges as well.
We got to talk about this. We'll talk about it in our group chat first. But when you said tend to precision,
Oh yeah.
we're talking about the mathematical practices.
Mhm.
And so, yeah, let's put that in our notes.
We're gonna put it. Let me write it down right now so I don't forget.
Because there's some things that I think are important that teachers don't always get the opportunity to get into in regards to the mathematical practices. We do many of them often, but I think if we were more intentional sometimes, and there's different barriers to that, but yeah.
Oh, that's the next episode right there. Mathematical practices. Mathematical practice. That's it. Because structure, if kids pay attention to structure, there's so many different ways for them to. Matter of fact, we're gonna get into something where structure is gonna be a key. Like if you pay attention to structure, it's gonna really make it a lot easier than what it may initially present. So when we get there, I'm gonna see if y'all think about it. Okay. Kakil, did you want to add anything before I go to the next one?
Yeah, a couple things. So one of the things that I started thinking about when you said the letters, the capitalization or the lowercase status of the letters matters, I started thinking about standard form of an equation, ax plus by equals c, and you know that capital A. Well, I think about the b specifically. The lowercase b, of course, would be the y-intercept, but in the standard form, the b should be capitalized because you know that's the coefficient of the y. That definitely like it transcends a lot of different topics. Also like when you were talking about what you have on the screen, volume being the capital B times H, the area of the base times the height. It makes me think about the cylinder, like the formula for the cylinder, the volume of a cylinder, because the cylinder is just a bunch of circles stacked on top of each other.
Yep.
So again, conceptually, that's why it's like it's because I hope for like children to be like, wow, like okay, so this formula for the volume of a cylinder is very similar to the formula for the area of a circle.
Yep.
It's just that now you just multiplying it by the height, and it's like, yeah, you're doing that because it's like a whole bunch of circles stacked on top of each other. So you got to multiply to figure out like how tall it is, right? And the other thing was, damn, what was the other thing I was going to say? I lost it. I lost it
Are
just
you
now.
thinking about it? When you brought up the cylinder and its relationship to the circle, I'm gonna bring up the cone and its relationship to the cylinder. Because if you do that little activity where you're taking the liquid and you're pouring it into the cylinder or vice versa, you'll notice that the cone is 1/3 of the cylinder.
Yeah.
You know what I mean? So like giving the students an opportunity to see that relationship, I think it makes sense because now, okay, boom, as soon as I know how to find the area of a circle or a cylinder, I'm just taking into account the layers. So that's the height. Oh, a cone, that's 1/3 of it. Like I don't have to remember all of these separate formulas. It's one. It's literally one. And then I'm just thinking about relationship.
And parents, real quick. To the parents, real quick. I want to touch on what Lanisha just explained. If you have a little snow cone cup, right? That's a cone, right? But then you got a can of soup, a tin can, right? What you can do is take the two, fill one up, and measure it. Like. Of course, y'all probably don't have what they call them, graduated cylinders. You know what I'm saying? They probably would. I don't think you got no graduated cylinders at home, but at the end of the day, you can use like a measuring cup, for example. You know what I'm saying? So like you take that a smaller can, a little 8-ounce can. You know what I'm saying? A little small can tomato paste, and then a small little. If you don't have a um a snow cone cup, but something like that that is the shape, and you can show them if we pour the water from the can, okay, in this glass measuring cup. Oh, okay, well that's 1 cup. But then now you take that water and pour it back into the can from the measuring cup, and then now pour it into the cone, and you'll be able to see that there's a difference. You'll be able to see you can't pour all that water into there. So that's just things like that are home little what's the word in science? What do they do? My master's degree words ain't coming to me right now.
Experiments,
Experiments, or yeah, we'll use that term for
labs.
labs. So you basically can do a little lab at home with your kids to help them understand certain mathematical formulas. So now you're making it fun. It's not just they're sitting writing down pencil and paper and you ain't fussing, talking about them apples.
Mm-hmm.
Yeah, yeah. I remember what I was going to say. I was going to say like how conceptually the area is how many squares you can fit on a two-dimensional shape. Understanding that helped me to when you think about the volume, like what Dana was saying, how many cubes can fit inside of the three-dimensional object.
Mm-hmm.
Because then it's like, all right, so that's what I'm trying to do. I'm really trying to figure out how many three-dimensional cubes. And a cube, of course, instead of having two dimensions, it's got three dimensions. So instead of being 1 inch by 1 inch, length width, we got length width and height. 1 inch by 1 inch by 1 inch, or 1 foot by 1 foot by 1 foot, 1 yard by 1 yard by 1 yard. So we just trying to see how many can fit in there. So and then the number we get, because for our answer means, okay, so that means I should be able to fit this many. If my math is correct, I should be able to fit this many of those cubes inside of that shape, no matter what the shape is.
Conceptually, what comes to mind too, I think about a yard with a fence around it. We're gonna act like the yard is a rectangular yard. How much grass do you have to go out there and cut with a lawnmower? That's area.
Mm-hmm.
But if it's pouring down raining outside, right? So if we imagine, if water filled up your backyard, you know what I'm saying? Or if you just got like a little rectangular pool or something like that. But for the sake of the yard thing, hey, how much space of grass do I have to cut versus, or how much water is it going to take to fill up, or sand? If I filled up my backyard up the gate with sand, how much? There's going to be a whole lot more sand to fill up my yard up the size of the fence than it is how much grass I gotta cut.
Yeah, so that would be interesting because now I can look at the area of my yard and the height of my fence.
Mm-hmm.
And so now we can get into figuring out how much sand or whatever it would take to kind of fill it up. Okay. All right. I see y'all. Okay. So last one like this. Now we talking about surface area. This is another one that has proven to be challenging for a lot of students, but I don't feel like it has to be. So how can we make surface area make sense?
Gift wrapping. But gift wrapping without all the extra folding of the paper on the sides, the folding and the cutting. You know what I'm saying? Like if we actually all of the stuff that we cut off, we're not counting that. We counting just the amount of wrapping paper that it takes to completely cover this gift box.
Mm-hmm. So if they know how to find
or the old barn painting activity. Have you seen the barn painting activity for sixth grade? Oh, so maybe they don't use it anymore. But early on in Common Core, there was this barn activity that we used to do with surface area, and the kids had to construct this barn using a net. And for you, those of you that may not be familiar, a net is just like if we took this rectangular prism and we opened it up and laid it flat. So they construct this barn, and the problem is centered around how many gallons of paint will it take to paint this entire barn.
When I think about when people do problems like that, I think about, do they say, is it one coat of paint? Is it 2 coats of paint? Like, like how deep we going here?
We just
got the
covering the
round
barn
ball.
with paint, and we gonna paint the ground too. Cause somebody might be the person thinking like that. They're gonna be like, wait, but we don't paint the bottom of the barn. You're right, but we're gonna paint the floor inside the barn too.
Got it. Okay, so once the kid understands area, so all we doing is covering the faces of whatever it is. So once they understand how to calculate the area of two-dimensional, they can just apply that to this three-dimensional figure. Okay, all right, bet. Okay, so let's shift a little bit. So
Hey,
your boy was in the chat, Akil, Professor Parker was in the chat, and he was talking about how he describes these exponential notations or these relationships, especially when the exponent is 1. So I wanted us to talk a little bit tonight about these properties of exponents, and let's make them make sense, because I really feel like kids start to work with this in elementary school when they're looking at scientific notation. But for whatever reason, when they get to 8th grade in math 1, now they out here like this. I don't know what you're talking about when they've been doing it for so long. So let's make it make sense, y'all. Whoever want to jump in.
First of all, we must understand that those individual terms, x to the second power, is x times x.
Okay.
And so x times x means x to the second power, right?
Okay.
So then, if under that, I want you to write x to the third. Well, x times x is x to the third power.
Got it.
So now the rule, if we look at on the left side of the two equal signs, although it's like at the top we got 2 x's, at the bottom we got 3 x's, right? How many total x's do we have? 5.
yeah.
So when we multiply x to the second power times x to the third power, we're thinking of how many total x's do we have?
Okay. Anything you need to add on, Akil?
This just reminds me, and I think that, so again, throwing myself on the sword, like, and I realized like the error of my ways in the past. I was real big on like just teaching the properties, going straight to the properties. Listen, memorize the multiplication property, add the exponents, memorize the division property, subtract the exponents. And then I'm like, oh, that should make sense because addition is the opposite of subtraction. So multiplication is the opposite of division, right? But, and as I'm thinking about this in light of some of the conversations that we've been having about order of operations, but how order of operations is not really taught. A lot of times PEMDAS is taught. And I'm like, damn, I was essentially doing the same thing by not, because like it would be like, I remember times like explicitly like being in a situation where I'm looking at my textbook and I'm like, how they doing all this x times x times? I'm like, don't nobody need to know all that. Like, let's
I ain't got time for that. Boom,
Hey, I'm guilty with you, Akil. I'm with you, brother.
But what I didn't understand was like, again, I'm looking at it from my own level of understanding, which is ludicrous, basically, right? You got to really show it. You got to show it like that. You got to show it the long way and the conceptual way. So you'll see, so the student will be able to see like, yo, like, okay, this is why the property is a gift. The property is the shortcut, but you're not going to appreciate the shortcut until you went the long way,
Right.
And then, so for parents listening to this, I want y'all to understand that the conceptual, like what the Common Core does is it pushes the conceptual first, and then you get introduced to the quick algorithms and everything. But the algorithms will make sense once you already know the concept. So the multiplication property of exponents makes sense because we know this. And then you can even say, well, okay, I appreciate the multiplication property because if I had to multiply x to the 48th power times x to the 95th power, right? I'm glad that I don't have to write x times x times x and have 48 x's and then have 95 x's. And then I got to count them all up. I know that shortcut, the property is a shortcut. The division property is a shortcut. The power of a power rule is a shortcut. A lot of these are shortcuts, but just understanding that, you gotta do it the long way first in order to to get a better understanding. I think about like polynomial long division, and kids get mad like when you teach them synthetic, That's the way he teaches this in the first place. Well, you can't use synthetic division for everything. Not every divisor, but that's one reason. But you'll appreciate it better. You appreciate it better if you once you do it the long way, and then you see the connection between the shorter method with the long method that you learned in the first place.
Right.
Something comes to mind too that Akil just made me think about. Going back to what I just explained, we have to remember that this variable x by itself, or any number by itself, is taken to the 1 power.
Mm-hmm.
There we go. So we can essentially write a 1 exponent on each of those x's on the left side of the equal signs.
Okay. And I think this is what Akil was talking about in the chat, is the way that you present this, the number of times that you see the base in a multiplicative expression.
Multiplication, either expression or just a sentence. I just say multiplication sentence, because what a lot of books I've seen over the years say, and I'm working with a young brother tutoring. We're still reviewing his math packet from the summer, because there's a lot of content on there that he still needs, like, to get a firm grasp of. But in the packet, it says, like, what is an exponent? An exponent tells you how many times a number or term is multiplied by itself.
Right.
And I strongly, vehemently dislike that explanation of it, because it's just not true. Because then it doesn't stand up to scrutiny. Because then what about x to the first power?
Exactly.
If you tell me that means, like, well, let's use an integer. Let's use 6 to the first power. Because if you tell me an exponent tells you how many times a number is multiplied by itself, so if I'm multiplying 6 by itself 1 time, that's 6 times 6. So then by that logic, 6 to the first power should equal 36. But it don't.
All right, Terrence Howard.
The language is, he probably would say it that it equals 36.
He would based on that definition.
Yeah. Right. So I'm like,
1 times 1.
So I had to come with we got to come with a better definition. Like, so I'm like, look, it's a multiplication sentence. It's a multiplication statement. And first, what is your base? We need to know what a base is, right? Know what the exponent is. The exponent tells you how, because using the exponent, again, it's an abbreviation. It's so if you got to multiply x by itself 47 times, that would be 48 x's altogether. Instead of having to write 48 x's, we can write x to the 48th power, right? So, so just to be clear, because I'm sure, like, it's got to be students out there that have been confused by that. Because if they're anything like me, and they, take definitions in math class literally, then they'll get it wrong. And then they'll be like, but this is what you said. You said this. So 6 to the first power should be 36 based on your definition from this book, or the definition you put on the board. But I think that also comes from teachers not really examining what it is they're saying, and thinking about what it is they're actually, and what they're telling children actually makes sense. Like, they might have heard it from somebody else, and they might be, and then also it's one of the things where it's like, a lot of times, because you know how it be, like, we know what we mean, but we might not be as precise in our explanation. But and a lot of times people know what we mean when we say it, even though it's not as precise and it's not even as accurate. But, like, you know what I meant. Like, what I'm saying? It's one of them type things, but everybody don't know what you mean.
Yeah.
So that's why I'm like, over time, I've become very big on trying to give very precise and, like, specific, like, definitions, as specific as possible.
Yeah.
So to avoid the confusion.
The other day when you brought that up, I was like, I don't want to be Miss Me Too, but I remember a time where I was given the definition for, just bases and exponent and things like that. And I thought about it, I was like, that don't really make sense. But I've read it so often. Like, when you Google it, you go to all these different math works websites. When you go into these books, when you look into, like, glossary, when you look it up, that's what it says. So I'm like, ain't no way I'm smarter than them. They've been doing this, so they got to be right. So then, even though in my mind it don't quite make sense, I still said it. Or even if I didn't say it, I still went with it because I felt like they got to be right. So I think that's one of those, that's probably an imposter syndrome type thing, or just feeling
Yeah.
like just because it's written somewhere that it has to be the gospel. And that's not always the case, because I found plenty of errors in even the unpacking documents. So, that's a good point. I want to talk to, I really want to think about that. I started Googling that the other day and I still can't find anything to the contrary. Like I can't find anybody that said anything different. So maybe everybody is like, well, that one person said it, so we all just gonna be on the bandwagon with them.
And it was a
And all
black.
it takes if they got the PhD in math from a certain school and then they've been teaching for a certain number of years, it's like
This
I
is
don't
what
want
it
to
is.
I don't want to challenge them.
But that's
Even though
also
they be
that's
wrong.
also the very reason why we have this issue, I believe. Because if we just think about just one state, right? Let's pick a random state, Texas, very big state,
Okay.
tons of colleges and universities
Mhm.
that have trained thousands of teachers. But let's just say hypothetically, there's 300 colleges in the state of Texas that all have teacher education programs, right? And then within each of those colleges, there's multiple math teachers or education teachers just on one of those campuses. Like we talk about lateral vocabulary and the lateral progression of vocabulary terms within one campus, just like we see it on the campus of a public school. The same thing is going to happen at a university. You see what I'm saying? So that's why we have all these different, some terminology is not explained as well in detail because like you said, Akil, a teacher is probably going to teach it based upon the way that they learned it.
Yeah.
Whether that was coming from a teacher or whether that was coming from the way that they had to go study themselves to get a better understanding of it.
Random, and then we're gonna get on topic. So similarity. Whenever I don't know if it was necessarily when I was coming up or the last memory that I have of it, whatever age that was. For some reason, I felt like it was so complex, like it was a whole bunch of acronyms and letters and all this stuff. But it's so simple. Like I just remember a whole bunch of AAS or ASA or
Mhm.
something, a whole all this stuff. I'm like, what are we talking about? But it's so much simpler than that, in my opinion. It just don't seem like it's that deep for all them acronyms that they were given. Maybe I'm oversimplifying it, but when I think about congruence and similarity now, it just don't seem as deep as what it was presented to me. As
Oh,
difficult.
I always thought that through my undergrad program. And like even now I'm teaching math too, and my next unit is congruence. And I'm like, already I've looked at the assessment and I'm like, okay, I'm gonna have to get in my bag to get these kids to understand it because I think a lot of times they're gonna look at it like side, angle, side, angle, angle, side, angle, side, angle. Da, 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 da.
Share
Yeah.
it with me. Give me the test too.
Hey,
Because
I will. Yeah, I will.
I mean, they already starting to learn it in eighth grade. We already starting to talk about that in eighth grade. And I just don't, what I'm seeing, it does not seem as challenging or difficult as it was once presented to me. But maybe I'm oversimplifying. Send me the test. Let me take the test. If I pass the test, then I'm standing on business. But if I fail it, then you don't tell nobody. Okay.
When you look at that test, you're gonna be like, what? Okay. I
I
gotta take
just
it first though.
I just remember there was no ASS similarity theorem. I just
Correct.
remember
Right.
like
That's it.
everyone except
Correct.
for that. Is that
Yeah. All right. Okay, so we already kind of talked about this a little bit. So I just want us for these next 3 slides, which goes through these properties, I just want us to just map it out in a way that is clear so that people can make sense of what it is that we're talking about with these properties. So whichever one of you guys want to do it, I'll annotate and you guys just lead the way.
I'll take it. 5x is on the top in a fraction. Let's do a fraction bar. Yeah. All right. And you can choose to write the ones or not. I actually don't write the ones this time.
Okay.
Fraction bar under those, and 4x is under that. Now, in a fraction, whenever you have the same numerator and denominator, it equals one whole. So any number divided by itself equals 1, right? So boom, 1, 1, 1. So we're left with 1x on the top. We can rewrite that under there. I want you to write 1 times 1 times 1 times 1 times x. And 1 times 1 is 1 times 1 again is still 1. So however many times you multiply 1 is going to be 1, and 1 times x equals x. Now, if we want to, we can go back and say, oh, well, that's x to the 1 power, or just x.
Which leads us to this property where if the bases are the same, we can just subtract the exponents.
The numerator subtracting, because we got to be specific. We take the exponent in the numerator and subtract the exponent in the denominator.
Yeah, top down. Follow
Yeah.
gravity. Yeah. Yeah.
Yeah. Okay. All right.
So can I say something about that last problem? Like I'm thinking about like when you know all of the properties, and then when you know all the properties, then you can kind of like, I don't know, like, and I want to push this idea because this kind of gets into the different perspective on math, and like, because math really can be fun, right? It could be like a game, because if you know all the properties, then you might want to get a little freaky with this. You might want to say, well, what if I take the x to the fourth, use the negative exponent property, swing him up to the top, and then make that x to the negative fourth power, and then use the multiplication property and then add the 5 and the negative 4. That's going to give me x to the first power. So it's like, as a student that, you might have that student or some students in your class that just like, they get it. And then they treat it like a game, and they're like, all right, well, let me think of how many different ways I could do this. Or what if you move the x to the fifth down to the bottom? And then you make that, I mean, somebody might say, somebody that's not into that, doing more than they need to, might say, well, you're doing too much. This too much. You're doing the most right now. You're doing the most right now, right?
Mm-hmm.
But you just as a way to just play around, and just, it's a way to reinforce the rules and understand the rules, because you swing the x to the fifth down to the bottom, then you got 1 over x to the fourth times x to the negative 5 power, and then you do the 4 plus the negative 5, then you got 1 over x to the negative 1, then use the negative exponent rule, swing it back up to the top, but just different ways, like, once you know all the properties, then you can kind of play around with it, and then as long as you get the same answer every time, and I think that's the beauty of math, like, you get the same answer every time, like, no matter how you approach it, as long as you're using the property correctly and applying it correctly, then you get the same answer every single time.
I think that's going to help students too. There's so many teachers that have been adamant about students doing things the way that they teach it. I think that message needs to be spread more, that, hey, if we're all starting at Cheney University, right, and we want to drive down to Bowie State, right, we can all take different ways.
Mm-hmm.
We still going to get to Bowie State.
Right.
Yeah.
One thing I was going to say about what Akil said earlier, that could be an extension activity. So like, once they find it one way, they finish early. Okay, boom, let's see if you can find another way to do this. And like you just said, we driving to Bowie or wherever we driving to, you getting the same answer, you just going about it in a different way. That's a way to extend them. All right, so let's look at this one.
I would put, we could do this 2 ways, but I'm gonna go the shorter way. So I would put x to the second power in parentheses. And then I will put x to the second power in parentheses again, and I will write that out 5 times. And so now, when I look up, if I add up all of the exponents in that, 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8, 8 plus 2 is 10, right? So I have a total of 10 exponents, right? And so now, and if you wanted to, just for sidebar, instead of writing x to the second power, in each parentheses, we could write x times x. You're still going to end up with 10 x's.
Mm-hmm.
All right. And so then the rule tells us when we have a power taken to a power, or exponent taken to another exponent, we multiply the 2 exponents to get the simplified version.
And why this should make sense We're trying to make this stuff make sense. This will make sense because we already understand the relationship between the base and the exponent.
Right.
The number of times that we see the base, I'm using Akil's definition, the number of times that we see the base in a multiplicative expression. So we know that we should see x squared 5 times. Therefore, that's x to the 10th power. All right. Last one.
I like this one. All right. So the radical or the square root symbol, for those that aren't familiar with the terminology, that radical actually represents an exponent. Somebody might be saying, well, what exponent does it represent? It represents 1/2. So I can take this.
Wait, can I ask a question?
Yes.
So if I'm a person, I hear you say it represents 1/2, and I'm like, well, where did 2 come from?
I'm about to break it down for you because it's the square root. And when we talk about square, going back to our original conversation, they use the term squared because they're thinking a square has 2 dimensions, right? So if I take that exponent that's already under that radical, x to the 2nd power, I'm going to write x to the 2nd power, and then I'm going to put it in parentheses. And then I'm going to put an exponent of 1/2 out there. So now if I am familiar with the previous rule, a power of a power rule, then I'm going to actually multiply 2 times 1/2. And when I multiply things like 1/2, I like to say, what's half of 2? You know what I'm saying? Well, 6 times 1/2, what's half of 6? Because that also helps with the terminology of that term of. So that leaves us with just x. So now I would always, I put the bow on this type of explanation to say, anytime I have the square root of a term taken to the 2nd power, the exponent of 2 and the square root symbol cancel each other out. Technically, it doesn't. It just multiplies to be 1, as we can see right there on the screen.
So then if this was a 3 here, that index was changed to a 3. Now we're looking at.
All right. So now we're talking about what number can I multiply by itself 3 times to get whatever is under that radical symbol. So whatever that index changes, let's say if it's 4th, I'm trying to figure, if I want to know what's the 4th root of 64, what number can I multiply by itself 4 times to get 64?
Okay. And I can rewrite this.
Then let me ask you a question, because you reminded me of something that, like, my 11th grade, I think I was taking a class they called math analysis. It probably was like a pre-cal class, actually. They just gave it a different name. He was like, you're not actually canceling out. So tell me more about that. Like, when you say, like, you're not actually canceling, because I think he was saying there's a difference between canceling something out and dividing something out.
I love that. What I grew later on in my career to realize is, because I agree, it's similar to what I said in those other examples about, like, when we were doing the quotient rule. Any number divided by itself is equal to 1. Right? So a lot of times math teachers have been taking that concept and just saying cancel it out.
Right.
You see what I'm saying?
Yeah.
So I think that it's just one of those things that people said over and over again, and people took it and ran with it. And after a while, finally somebody said, wait, hold up, I don't understand that. What do you mean cancel out? You know what I'm saying?
So cancel out is just for equaling 0?
That's a good question. That's perception. For somebody, it might equal 0. For the other person, it might be 1. That's why I told you to write 1 times 1 times 1 times 1 times x. So once again, it's perception. And with this new generation of students, everything is relative, just about. Because, like they say, like I started saying, common sense ain't so common. Because what was common in your household growing up, Akil, may not be common in my household. You know what I'm saying?
Right.
Yeah.
Okay. All right. So the reason why I drew this little square and I circled the side is because I was trying to relate what you were saying in terms of square root.
Mhm.
So we know that when we are finding the area of a square, you're multiplying the side length. So that would be s squared.
Mhm.
Then if I am working backwards and I'm finding the square root, now I'm finding the actual side length. So that's
Yes.
why I drew the square and circled the side length. I don't know if that made sense, but that's what I was doing.
I love it. It makes a lot of sense.
Okay, so we're gonna move past this because this next part is probably gonna be fun for the people when they see it, when they watch it. So we're gonna go here, okay, to evaluating expressions and really making use of structure. So I'm hoping that some things stand out. So I'm gonna give you guys a minute because I want us to make sense of this. Let's make sense of it.
Ooh.
What was that?
I'm seeing a way that I probably can't tell the people because I don't want them to cancel us. Because I kind of just like saw this in reverse.
Okay.
I see distributor property. You know what I'm saying? Because I gotta like if we think from the perspective of order of operations, right? We have to multiply before we add and subtract. So I would circle, yeah, there we go. So I got 3 times 15 plus 4 times 15 minus 5 times 15. Boom. And so in parentheses, I would put 3 plus 4 minus 5. All right. And so now if we go inside the parentheses, 3 plus 4 is 7. And 7 minus 5 is 2.
Mm-hmm.
So I essentially end up with 15 times 7.
15 times.
2. 2. Oh, Lord.
So let me tell you something. So Akil, I don't remember when it was, but Akil was like, and you really don't have to go from left to right with addition and subtraction. And when he said that, maybe like last year or something, I don't know when it was. I didn't know him like that. I was like, so then I started doing all my little expressions like, oh, I'm about to see if I could just go ahead and subtract before I add, you know what I'm saying? Because I mean, subtraction is just the opposite of addition. Anyway, so
But you gotta carry the negative sign though. That's the
if
thing.
I
Like,
do 4 minus 5 and get the -1, 3 plus -1 or 3 minus 1 is still 2, and 2 times 15 is still 30. So I was like, this is what I'm saying about being robots. I feel like whenever I was in school, I was programmed to be a machine. Like they taught me what the procedure was, and I followed it blindly. It
Because
was
they
not
was
until I
teaching
was
us,
an
they was
adult.
teaching, you got to think this school structure
Yeah.
came about when they was when the industrial era came about. So they was trying to produce workers to go work in the factory so that, okay, you the shift lead, you the team lead, you tell me, Akil, and these other 5 people on the team, I need y'all to just do this, and this.
You had one job.
I was about to say that, Nick. Hey, you got one job. And all I need you to know is how to do that job.
Right. The problem is though, like it's like when things go haywire, when the machine break down, and then you got to be quick on your feet, and you got to have critical thinking skills to
You
learn
got
to
it.
know what to do to literally like save lives. You know what I'm saying? Like you
Yep.
said, you don't got it because you wasn't trained to do that.
That's a very consumer mentality. I don't want that. I don't want that. And I feel like this is the reason why I ain't no millionaire yet, because I've been trying to unlearn how to be a consumer, how to be this machine and just do these procedures. Like when I'm learning this stuff, like I don't have to do it this way. I can do it another way, and I'm gonna still get the same answer because
That's
I
capitalism
understand what I'm
too.
doing.
Yeah, that's capitalism. And my aha moment was, man, shout out to Spring Hill Middle School, my students from Scotland County, man. My aha moment was I was just going through, had them working out a problem, put a problem on the board, going through, checking their answer. And it was one kid, I can't even remember their name. I was like, nope. And this kid advocated for himself. And he was like, nah, this is right, Mr. Harris. So at first I was going back and forth. I said, all right, I'm gonna look at it again. And I looked at it again, and he just took a different route. And I was like, yo, I gotta apologize in front of everybody. And I think that was 2006, 2007, right? That changed my career. You know what I'm saying? That was early in my career. But that changed the way I taught from then on. So after that, like even now, I said it to my students again today. I'm not a tyrant as a math teacher. If you can do something a different way and you can show the work to support it and explain it, I ain't talking about you just went and Google something. I ain't talking about you just went the math way and you paid a couple dollars for it to show you all the work and all the steps. No, if you can show me how your brain, you might be left brain and I'm right brain, but you can show me how this works logically and mathematically, I'm with you, dog.
Yeah.
Can I ask you a question? Like, cause this is something that, like, you know, in terms of people feeling like they may or may not be math people and utilizing that terminology. So Dana, when you looked at the last problem, how did you know, or what is it about you that enabled you to know that you could flip that into like a different type of expression using the distributive property?
In my mind, I saw 3 multiplication symbols, and I know you got when I saw multiplication, addition, and subtraction, I know multiplication supersedes addition and subtraction. And so in my head, I said 45 plus 60 minus 75. Right. So then when I said that in my mind, I'm like, oh, okay, well, what's the common number between, if we separate the addition sign and the subtraction sign, what is the common number in those 3 expressions, if you will? Oh, well, the common number is 15, so I could pull that out.
15, you can factor it out, basically.
Exactly. Yeah. So now that I pulled that 15 out, oh, okay, I'm just left with the 3. So now after I pull the 15 out, the multiplication symbols are gone. Right? Because I essentially did the opposite of multiplying and dividing when I pulled that factor. So I divide 3 times 15 by 15, 4 times 15 divided by 15, and 5 times 15 divided by 15. So we're going to put it on the outside. Still got some things in parentheses. Can't just leave the babies in the car in the hot sun. So now, who are the babies? I got 3 plus 4 minus 5.
Why are we talking about the babies in the car?
Yeah. But further, what I want people to understand is that I'm sure you would also agree that because you have a lot of experience working with problems, you have a lot of number sense, you have a lot of fluency and familiarity. You're able to see that, because what happens is, like, so let's say like somebody's watching this, right? And they're like, damn, how do you know to do that? Like, you know what I'm saying? He must just be so much smarter than me. I would have never thought to do that.
Repetition.
Exactly. Repetition. So if you're a person watching this, if that didn't jump out at you, then that's not an indictment on your intelligence. That doesn't mean you're less intelligent. That just means you don't have a repetition yet, and you just haven't had enough experience, right?
I've been sharpening my axe, just hitting that same spot.
Yeah.
And technically, although I only been teaching for 20 years, we add 4 years of college. So technically, I really been doing this math thing since I was about 3 years old. So we talking about, I've been looking at math and doing math going on 40 years.
Right.
So that's why this stuff jumps out to me. So when you're a child, when you're a student and you're in 6th grade and 7th grade, you may, let's say you didn't have a heavy education push in your home. So let's say you didn't start really looking at math thoroughly until, I'm gonna say 5. You knew your numbers, and most kids know their numbers. But from 5 to what, 11? If you only been looking at this stuff for 6 years, compared to my 39 years, you're not gonna see it the way. So that's where teachers, we gotta also remember that. In the classroom, I'm reminded of that daily. I will say something, and then I'll catch myself, and I'll say, wait, let me ask a better question. Because I realize sometimes my question go over their head. Rewind. Let me ask a better question.
Yeah. I like that. Okay. So let's apply that same thinking, all of that you guys just talked about, to this expression? What do you notice?
They all have the same thing in parentheses.
Yeah, that's my common factor.
Okay.
Yep.
So then now what?
I would write that one time, and then in parentheses or in a group 5/2 x plus 6 1/2, the quantity of that, and then I multiply that by 3 plus 4, quantity of 3 plus 4 minus 5.
Okay. And
I
we
would
already
do
figured out what
the
that was, right?
Yeah, 2.
Exactly.
Mm.
Okay.
Going back to our good friend, right? And I want kids to understand this. Going back to our good friend that a number divided by itself equals 1, right? Imagine if we wrote that 2 as a fraction, 2 over 1.
Okay.
So if I got a 2 in the numerator and a 2 in the denominator, boom, my 2's cancel out when I'm multiplying 2 times 5/2, so I'm just left with 5x. Same thing happens in the second term. If I got a 2 in the numerator and a 2 in the denominator, those 2's cancel out, and I'm left with the 6.
All right. So we got 5x plus what?
6.
Those you gotta we doing 6.5 times 2, right?
Yeah.
Or you thinking about it in terms of like if you converted the
6
6
halves.
to an improper fraction?
You know what? Rewind. Cause I'm looking at it as 6/2. That's now. Side note, that's how sometimes when you've been doing this for a long time, you can see stuff before you could get ahead of yourself. So in that case, if I could break that 6.5 in 2. Okay. So I got 2 times 6, which is 12, and then half of the 2. So 13.
So this summer, me and the kids was looking at why 6.5 ends up being 13 halves. And it was so interesting to see their light bulb go off whenever we created the diagrams for it, and they were able to make sense of the fact that it's 13 halves. Very, very interesting. We had somebody in the comments say, "Oh, I see fractions about to log off."
Oh
Feel like that.
man, no, don't go.
I don't want people to feel like that. I want you to see fractions and be like, "Oh, I got this," because a fraction is a number 2. A fraction is a number 2.
It is a number.
Absolutely.
It's a number. Because when you're trying to lose weight, if you lose that half a pound, trust and believe, you gonna pat yourself on the back.
I'm gonna celebrate, even if it ain't a half a pound.
If I get a half
a
an
pound
inch less in that belt loop, we gonna celebrate.
Yeah, take it.
Right.
Take what you can get.
Yeah. All right. So we looked at expressions, we looked at area, we looked at volume, we looked at surface area, we looked at properties of exponents. Now I want us to get into equations, and this is kind of where we're going to end the night with this type of section. So again, the whole phrase for all of tonight has been make it make sense. So what we got here?
W minus 2 5 times. And they all add up to 40.
W minus 2 5 times, and it adds up to 40. It totals to 40.
Yeah.
Okay. So we're solving the equation. So now what could we do
to solve?
Yeah.
Oh, well, I listen, I like that 5 on the outside. He trying to get inside. Nah, we ain't gonna let you in, man. But guess what? We're gonna send you around the back door. So remember, when you got that number in front of the parentheses, if there's nothing between the number and the parentheses, that means multiplication.
Okay.
Well, if I'm trying to get that variable W by itself, I need to get everything else away from that variable that I'm solving for it. So everything that's on the side of the equal sign is that W, they got to go. Well, what's the opposite of multiplying by 5? Divide by 5. We got to keep this thing balanced. We want to be equal opportunists. So now 5 divided by 5 is 1, right? So I'm left with the W minus 2. 40 divided by 5 is 8. All right, we still trying to get Dub by itself, man. Mama wants some peace and quiet, kick all the kids, the husband, everybody out. All right, what's the opposite of subtracting 2? Add 2. We still got to keep it balanced. So now, -2 plus 2, and I always write that line through them so they can see they're opposites. So opposites make a zero pair. So now we got the W equals 10.
Mhm. So we use those tape diagrams because we want students to relate the fact that that factor of 5 relates to the quantity W minus 2 being added to itself 5 times. So we're trying to relate that because, as I think we've talked about this before, sometimes you'll ask kids, they might see something like 5W. You ask them, how many W's do you see? And they say, I see 1. But there is 1 W here, but this represents 5 W's. And I don't think kids always make that connection. So that's why we use the tape diagram for the kids to be able to see that. All right. So there's some
like
people.
this.
Go ahead.
Can I jump in? I like this too. And I like the idea of teaching consequential thinking through the use of algebra. And not just algebra, but really any type of math problem, because it's kind of like it's a life lesson. Like, I teach my children, you know what I'm saying? Like a lot of people teach their children, actually more people should probably do this, but that you are free to do whatever you want to do, but you will never be free of the consequences. So with a math problem like this, like if we decide to divide by 5 on both sides, there's a consequence. We end up with W minus 2 equals 8. But if you decide to distribute the 5 into the W minus 2, you end up with 5W minus 10 equals 40. Then there's 5W minus 10, there's a consequence to that. And not so much in this problem, because I see that as kind of an equal amount of work. But I was tutoring somebody the other day, and it was like one of those equations where you got a variable on both sides, and it was 4 terms. And she was like, well, what if we divide by 6? And I'm like, okay, you can do that, but then you're gonna create all these extra fractions. It's probably gonna get real messy. Right. But you can do that if you want to do that, but just be prepared. So it's like there's a consequence, right? So that's another thing, like think about, like, so you can teach your children character and certain life skills, and so then they're thinking like, okay, every time they sit in a math class and do a math problem, they're thinking about, all right, well, what's going to happen when I do this? If I do this, then what's going to happen? If I don't do this, what's going to happen? Like, what are the consequences? Right. So, and then every time they sit down to do a math problem, they think in that way. Another thing I wanted to say, Dan, you mentioned zero pairs. Mm-hmm. I never learned about doing integer arithmetic with the zero pairs, with the number counters.
Me neither.
I learned that last week. Asada came home with some homework, and the teacher was teaching it that way, with the circles with the plus signs and the circles with the minus signs. Mm-hmm. And I was like, what is this? Like, right? Yeah. So, but I never learned it that way. But then once I got into it, I'm like, yo, this makes sense. And I actually recorded a video for my channel earlier today. And I realized that, okay, so I always, how I ad lib on my videos, because I already know it's going to be people watching it like, why we got to do all that? What we need to do? Why can't we just do that? I'm like, listen, it finally occurred to me, like, these are training wheels, right? These are training wheels, right? Eventually, your child going to be able to add and subtract positive and negative numbers mentally off the top of the head anyway. Like -4 plus 6, they just going to know that that's 2. You know what I'm saying? Like, they're going to know. See the double negatives, they're going to know what to do. But when they're young and they may not be as familiar with the arithmetic with integers, like, learn as many different methods as possible. If they got to do the zero pairs with the number counters, then it's fine. Like, embrace that, and again, treat it like training wheels. Put the training wheels on the bike when they first get the bike for their birthday or for Christmas or Kwanzaa or whenever, when they 5 or they 4 or whatever. But eventually you're going to take the training wheels off. They just going to ride. They're going to be all right. And they use any method that they want to use. Like, so just, if you're a parent listening to that, just listen. Like, don't get frustrated. Like, it's going to help develop a conceptual understanding. It's going to help to develop the conceptual foundation. And then they can learn all the algorithms and everything. Well, they'll be learning the algorithms at the same time, but at least the algorithms will make more sense if they have the conceptual understanding as well.
Somebody asked in the chat, does it matter to know all the ways as long as you get the correct answer? To that, I say, they might not know all the ways, but I do think that you want kids to be efficient. Mm-hmm. So some people, when they see this, their first thought may be, let me distribute. Mm-hmm. But that adds on, to me, I think it adds on extra steps.
It does, yeah.
So if I recognize that the quantity on the left side and the quantity on the right side have a common factor, I'm going to use that. And I'm going to get to the solution in fewer steps. And I think that's what we want students to be as they are packing their toolbox, as they are getting their training wheels and becoming more proficient. I think we want to get them to the point where I can choose which strategy I'm going to use because it makes more sense in this situation. Would y'all agree?
It makes me think about what Akil said, that equation with variables on both sides, right? I always tell students, you got 4 different terms. You can move any one of these 4 terms to start this problem. You're still going to arrive at the same answer. But for me, in my head, I'm going to move the variables where it's going to end up positive. Because I don't want to have to divide by 1, and I don't want to have to explain to the kid. I think I've seen so many kids that could get it down there and they got that negative variable. It might be like negative x equals 5. And I will say this is just like saying the opposite of x equals 5. But let me show you what that means mathematically. There is technically a negative 1 in front of this, so we still have not gotten the variable by itself.
Yeah, it's like you're not done yet. You're not done yet.
Right.
The X, and then they think like the negative sign is kind of like immaterial. So it's like,
Yeah.
all right, cool, we done.
So I'm gonna give you guys an opportunity to answer this question. So we got another comment that says, yeah, I'm going 0 to 100. Question, how much additional work should a child do at home? Can you give too much enrichment? I had more work time than free time when I was a kid, but I know they say things are different now. So what is your response to, is there such thing as giving too much enrichment at home, and how much work should we be giving kids at home?
I think that, yeah, you can. They do need a break. But the first thing that comes to mind, because one of the differences between Akil and I is we both do math by standard algorithm. But what I love about Akil's YouTube channel that's different from mine is mainly standard algorithm math. His is real life math. So he's showing you how you can still give your kid that enrichment while you at the table feeding them breakfast, while you at the table eating dinner, while you in the car riding to the park, while you going to the store. You know what I'm saying? So in that regards, no, that's the reason why I'm an educator to this day, because that's all my granddaddy did. Everywhere, the world is a classroom. So I'm sorry, I'm about to rant.
Yes, the world is a classroom. Go ahead, Akil.
Let you cook. We want you to cook, brother.
Nah, that's it. I want y'all to get y'all thoughts in.
So I agree. I mean, it's too. There is a possibility to have too much. A lot of times I'm a heavy advocate for, like, you know, pushing the work and the enrichment and whatnot, because I think there's been a pendulum shift or pendulum swing back to the, well, no, just don't give them nothing. Like, kids just shouldn't do nothing at home. Like, once they out of school, they just be able to chill, be on the game, doing whatever, you know. And I think that's dangerous too. So I think we do have to, but as long as they're doing something consistently, daily basis, and I can't even really put a time on it, because certain skills, certain problems require more time than others. So I might say, okay, for this type of problem, if you go home every night and do like maybe 10 problems or whatnot, you know, you should be good. I mean, I kind of arbitrarily came up with this idea of just like 100 problems, you know, not necessarily 100 problems in one night, but 100 problems of every topic. I think that any child that does 100 problems in a topic and gets them correct and works through them, recognizes their mistakes, fixes their mistakes, you know, and they should be pushing proficiency, right? If they can do 100 problems, and if that means 20 problems in a 5-day period, if that means 10 problems in a 10-day period, 10 problems per day in a 10-day period, or like, I don't know, 15 problems in an 8-day, what's that, 8 days, 7 days? Yeah, like in a 7-day period, like, you know, as long as they get like 100 problems, because you can't go wrong with that. That's like you getting your repetition in, you know.
But are we talking, because for on behalf of the parents, you mean to tell me my child got to do 100 of these crazy word problems? So are we talking about word problems with application, or are we talking about 100 to where it's like what I like to call naked math?
I think it's just, I think if the problem is more rigorous, I think you might have to spread out the time horizon. You may just have to do less per day, because that word problems can be kind of, I mean, depending on what level the word problem is, I mean, you might be good with like, doing two problems in a night, or two or three. But the key is like it's frequency. The key is frequency. So if you're doing two problems, somebody might say, well, two, that don't seem like nothing. But if you're doing two every single day, then that's a lot because it adds up. And it's the cumulative effect.
Right.
Like doing them two problems, even if you did one problem, like that's better than nothing. A lot of times people just going home and doing nothing.
Right.
Like what's 0 times 5? So in a week you did 0 problems versus 2 times 5 or 3 times 5, right?
Yeah.
So I think that's the key. But I think to the parent that asked that, like, I don't know if it's necessarily an exact science. Maybe it is. If it is, I don't have the exact science on that. But I think it has a lot to do with you knowing your child, knowing your situation, knowing your household situation, and what can you support. But just try your best to have them doing something. Have them doing something. And also, even if you can, go above and beyond what the school is providing or what the school is assigning them, because I wouldn't want the school to be the standard, because you never know like what the school's idea for your child is.
Mm-hmm.
And if they can do more, let them see if they can do more.
Yeah. Okay. Okay, well, this is going to be our last one for tonight, and then we'll give our final thoughts and we're going to wrap up. So I did want us, we don't have to do every one, but I did want us to look at these hanger diagrams, because this is a way to conceptualize the steps that you take in solving equations or finding a solution. So you're looking at this hanger diagram as if we're talking about something being balanced, right? You could think about hands-on equations. You could think about something as simple as hanging up clothes in your closet, and you don't want it to be leaning from one side. So we got to keep it balanced on both sides. So with A, if we're talking about balance, what would be on the left and right side of our hanger?
X plus 3 on the left equals 8.
Yep. So then if I am trying to figure out the value of the circle, what would be a logical step that you could take based off of this hanger?
If I break the 8 down to, let's say, 5 plus 3, because I want to match that 3.
Okay.
And whatever matches, we can get rid of it. I don't want to use the wrong terminology, but if I got the same thing on each side, remember the values. I don't want to use the wrong term, but because I got a 3 on this side, every number or every term that's on both sides of the hanger that matches, we can pull off the hanger.
And I want to go back to what you said earlier. So if we're trying to figure out what X is, or the weight of X, we want X to be on the side by itself.
Mm-hmm.
So now what is on the side with X? That's 3. Because then when you start getting into the 5 and the 3, now we're talking about decomposition. And some students have that skill.
Yeah. Okay, let's approach it in a different way. So if we have X plus 3 equals 8, right?
Mm-hmm.
So in hanger terms, right? Some number plus 3 equals 8. What is that number? What number can I add to 3 to give me 8? And so now when I think about it, I'm like, okay, if on this side I got an 8, on this side I got some number plus 3 equals 8. Now I got to go into my number sense bag and say, 5 plus 3 equals 8. And depending on the numbers, you break that down. So now when I say, oh, well, 5 plus 3 equals 8, well, guess what? I got a 5 and a 3 on the right. I got an X and a 3 on the left. Okay, the 3 and the 3 matches. So that's how I wanted to say it. We can match the 3 and the 3. So what else is missing from the left side to match up with the right side? Oh, the X has to equal to 5.
Mm-hmm. Mm-hmm. Okay. B, I'm passing the ball to Akil.
Absolutely.
So I would do 12, and this will make a lot of students uncomfortable because they're used to seeing the variables on the left-hand side. But we got to get familiar with that too. Seeing the variables on the right-hand side. 12 would equal, I guess if I would write it out, I'm gonna do 2y. I'm gonna do 2y. But actually, no, because if I'm going from the hanger diagram, my first step, I'm doing y plus y,
Okay.
y plus y, and then I'm gonna combine that, and then so they can see, how this translates from the hanger diagram to what you have written on the screen, and then combine like terms. 12 equals 2y. But in terms of like the hanger diagram, so all I know how to do is get rid of the 2 by dividing by 2 on each side.
So I'm doing what to the 12?
You're gonna divide, so we're gonna cut the 12 in half also. We'll divide the 12 by 2. Divide by 2. Divide by 2. Yeah, divide by 2. Because divide in half and divide by 2, those are the same thing, or those are not the same thing? Divide.
Divide by 2 and divide in half?
Yeah. No, I think they
If I
are.
divide 12 in half, I'm gonna get 6.
We'll get 6.
If I divide 12 by 2, I'm gonna
By
get
2.
6.
You get 6,
I would
right?
be careful with that terminology because I agree it's the same thing. But once again, that the kids these days are very, very literal. You know what I'm saying? So I would say, oh, if I cut it in half, if I cut that 12 in half, you know what I'm saying? To me, I think that's more down their alleyway.
Because you
And
know what it is.
somebody, one of them smart people, like the dude that was arguing with you on the internet the other week, might have been like, "Oh, if you divide, he's gonna pull out the Webster's definition of it, and if you divide in half, then you're taking it to the, some craziness."
It's those
That's why I
prepositions.
teach in Ebonics too. Like I teach in Ebonics because I understand, hey, this is the mathematical language of it, but this is the everyday language of it. It's like every language. You got slang and you got the technical language. I work with a lot of students that English is not their first language. So kids from Venezuela got a different type of Spanish than the kids from the Dominican Republic. You know what I'm saying?
Yeah. And I remember now I'm thinking like, 12 divided by 1/2.
Oh yeah, no.
Yeah, that's
gonna
be different.
Yeah, that's definitely gonna be different.
Yeah.
Okay, so C, we can just talk about C and then I'll write D out. So C, all the students need to do is what?
Take that 11 and break it into 4 equal parts.
Yep. All right. And so now I want to look at D just because it has the fractions, and I know people are usually what is it, fraction averse? So yeah, I want to look at that one. So I'm going to erase what we have here so we can write out this last one. Maybe not. Just mess up my screen. I don't know what I did.
Let you be great.
It won't let me do it.
Man, come on.
I don't know what I did. Oh, here we go. We back in business. Okay. So tell me what to write and I'll annotate.
I'm gonna take 13 4/5 equals W plus 3 4/5.
Okay.
All right. So now, since we doing a hanger diagram, I probably would say I'm gonna decompose that 13 4/5, and I'm gonna take it and separate it to 10 plus 3 4/5.
Okay. Okay.
So the 3 4/5 are a match,
Mhm.
right? So they're a match. So then what's left? On the left side is the 10, on the right side is the W. The W has to be a match with the 10.
Yeah. So that would be paying attention to the structure. Like once you saw that you got 3 4/5 on both sides, then the other thing has to be equivalent, right? All right. So we done went through a lot. We was making a whole bunch make sense tonight, from area to surface area to volume to now ending on equations. I want to know, what is it that you guys are going to leave the people with tonight as we wrap up talking about how to tap into your math genes?
I know for me, kind of know we all have a vision for our children, whether we know it or not. And when we think about the vision for our child, or even what our child's vision for themselves, even when they're a crazy dreamer at 5 and say, "Hey, I want to go to the moon in a 4-wheeler," you know what I'm saying? You know what, DJ? You can go to the moon on a 4-wheeler one day. But I think when we think about that in regards to math, if your child really wants to do something that's going to be require a certain level of education, you got to be a forward thinker for them. And so you got to realize that the stronger their mathematical skills are, the better they set themselves up. Because you don't want them to get all the way to college. They done did very, very well, and they get all the way to college, and then because they struggled through college algebra or pre-calculus the first time, you don't want their spirit to be killed. You want them to have that tenacity and that will to say, you know what, dang, man, I got a D in this class, man. And it's a major course, so I need to get at least a C. Go back and take it again. I took physics 3 4 times at Fayetteville State University, but I wasn't going to let it kill my spirit because I had to graduate.
Yeah.
So I think that when you think about the push to be a better student at learning math, think about their future more than you think about the frustrations of the present and their struggles.
So I got three things to say. The first thing is something I alluded to earlier is when you're learning, when you have children to bring home the so-called new math, which really isn't new, but it provides a conceptual basis. Just think of that as training wheels. That's all it is. It's training wheels. Just getting your children prepared to understand number sense, understand the relationships between numbers, and it is going to ultimately make your children stronger math students. And not just math students, because we think about being a math student, that's just that could be limited to a classroom. We're talking about real life. We're talking about everyday life. Another thing is that I was at the National Association of Mathematicians Math Fest this past weekend down at Prairie View A&M, and just going down there, being around all this math professors and black math professors and black math PhDs and black math undergrads and whatnot. They presenting projects and different research they doing and everything. It just reminded me that the math education really shouldn't end. And I think that has to be like a paradigm shift that we got to really, push forth because, since math is kind of framed by our formal schooling, we think, okay, once I get to 12th grade, I don't never got to do this shit ever again. You know what I'm saying? Where in reality, math is something that we should be doing throughout our whole lives, and we should be learning throughout our whole lives. But what makes it difficult to be that way is if you never develop the love and appreciation for it. So as parents, one of the best gifts you can ever give to your child is a firm and solid foundation in arithmetic and algebra as early as possible. So just like, we pay for camps and we pay for this and pay for that, figure out a way to get your child strong in math early and often, and just so, they could do real life math problems. Like, I had to drop off my rented a car off Toro, and in the agreement, under the payment, they allotted me 300 miles. So I'm driving, this was my first time in Houston. I didn't realize Houston was spread out like Atlanta is or like LA is, like everything is all far away. Right. So I get back, I drop the car off and I'm like, damn, hold up. Did I go over 300? So I'm doing the math and I'm like, okay, I was at this many miles. And then I started out with this many miles. That was on the odometer. And I'm like, damn, I went over about 19 miles, but I remember it's like 58 cents per mile. But I was just sitting there just doing this like math and doing the calculation so I could just figure out how much over. I mean, I ended up being over by it cost me like an extra $11, which is cool. But I'm just thinking about the fact that I was able to just do that off the top of the head. And it's not because I'm a math teacher, it's just because I learned those skills, right? I'm doing 19 miles times 58 cents, but I didn't really do that. I've rounded the 19 up to 20. So I'm doing 20 cents times 58, but really I do 2 times 58 first. And then, you expand it because it base 10, then I multiply that $1.16 by 10, which gives me 11.60. And then because, it's what is that called? The rounding and compensating method, because it wasn't 20 miles, it was actually only 19. So you subtract 58 cents from that, brings you down to $11.02. And I know somebody listening to that might be thinking, oh, I'm sure when you was listening to this, you was like, that's too much. You're doing too much. I can't be doing all that. But it's from practice. And that's a real life situation. And I know oftentimes a lot of us, we find ourselves in situations like that, and we be mad, ready to cuss, ready to fight, because it's like, oh, what's this? What's this on my bill? Why? Like, nah, only because you didn't know how to calculate that. If you knew how to calculate that, then you be like, all right, it's cool, I get it, you know. But so so often, because we don't have those math skills, those fundamental math skills, we end up in these uncomfortable situations where, you know, stuff goes left. And that's how we want our children to already be able to do those calculations. And plus, it might be a situation where you might get charged for something that you shouldn't have to pay for. And then when you're able to do the math, then you're able to, like, you know, advocate for yourself and be able to, you know, make a claim and say, nah, like, you know, this, your math is off. I don't care what the computer said. Your computer's wrong. You know. So yeah, just those things to think about. Like, you know, the conceptual understanding is like training wheels. And, you know, the math shouldn't end. It shouldn't be something that we're trying to escape. It's not like an escape room. You know, we should be figuring out ways to try to embrace it, you know? So yeah.
So I agree with all that. I started chuckling because somebody said, exactly, everyone want to be an entrepreneur and can't count good.
Yeah. I mean, you see it all the time. You see it all
Oh God. Okay.
People think they try to they a lot of times people associate college, formal school with math and courses like that. And they say, well, I'm gonna just circumvent all that. I'm just go be an entrepreneur, as if you're not gonna have to be responsible for doing all that like on a daily basis anyway. Right. Like it's just flawed logic.
I'd rather take college algebra than to deal with the IRS.
Yeah, for sure. I want to take us back to the very first thing that I posted tonight whenever we began, and it was, I ain't got time for that. And all of us talked about, you know, where that could be coming from, what perspective that's coming from. And I really want us to think about the child, obviously, because we're all adults, right? Think about the children that we are leading, that we're guiding, that we're mentoring, whatever the case may be. And we really need to instill in them that you need to make time for it. Like right now is the time that you need to make time, because you don't want to be an adult trying to relearn things or learn things or worry about somebody trying to get over on you. And I really want kids to take a more active interest in the slow grind, because I think learning, that's what it is. You know what I mean? Like I'm going to take the time to learn today so that, you know, when I get older, when I graduate, when I go off to college, when I become an adult, I'm not having to worry about people taking advantage of me. Mm-hmm. And I feel like I can speak from experience, because whenever I was in school, a lot of things came a little bit easier for me, and I did not really develop a really strong habit of studying at all. So then when I got to college and I got with Miss Ragland and in that zoology class and I had to study, baby, I changed that major so quick. And it's something that I always regret, because I did not have good habits in place. I pretty much said, I ain't got time for that. And to hear Dana talk about the challenges that he had in physics, he did not let that beat him. And I think that's something that I often tell myself, that's what you should have did. Like, you should have not let that beat you. But that's the story that I'm telling my son. When you encounter something that seems challenging, that seems like an uphill battle, that is not a time for you to walk away. That is not a time for you to wash your hands of it and give up. That's a time for you to stand on business, as the kids say. It's time for you to really dig in and do what it is that you need to do. So I really want us to step away from, I ain't got time for that. And I need for us all to make time for that. And a lot of us are going to have to model that as the adults, so that the kids can kind of start to see that and then develop that mindset for themselves. Remember, a lot of times we're pushing our beliefs and stuff off on them. So if we start modeling it, maybe they'll start picking it up. Okay, so as always, I love it when we can get together and we can wrap it up, when we can help people tap into their math genius, because we all believe that it is possible for our kids to be successful in mathematics. I want all the kids to be successful in all this math, because we all are young gurus as we bud and bear fruit. Until next time, y'all. Peace.
Peace.
Peace.